Hello everybody, this is the second part of our video lectures on RSA, and here is a presentation of the fundamental theorem of RSA, which is a very important, by the way, and will help us understand how the key system is built and why RSA is a secure crypto system, and also why it's an asymmetric system. So let's start by the beginning. Actually, we will take an hypothesis which is necessary to RSA is to consider some n integer number as a product of two different prime numbers named p and q. So before I present the theorem itself, let's just make a little reminder about phi of n. Once again, we will use phi extensively through this chapter. So phi of n is phi of p times q. And actually, as p and q are prime numbers, they are coprime, as they are different. So the GCD of p and q is equal to 1, which allows to write that phi of p times q is phi of p times phi of q. And also, as p and q are prime numbers, phi of p is p minus 1 and phi of q is q minus 1. So that's quite easy once we know which numbers p and q are used to calculate n to get phi of n. Phi of n is p minus 1 times q minus 1. So now let's go to the fundamental theorem of RSA. Actually, we won't use it in the form I will just write down in a few seconds, but from this theorem, we will get a very interesting property used by RSA. So the theorem is the following. For all a bar element of z over nz, a bar to the power of k times phi of n plus 1 is equal to a bar, where actually phi of n, we know how to get it. And here, k is a positive integer number. So actually, this is in this form, the theorem is not really suited for RSA, but what we'll get from this starting point is the following thing. So I'll make a quick proof just after. So if one chooses some e integer numbers such that e is coprime with phi of n, that is, their GCD is equal to 1, then there is or there exists d, which is also in integer numbers, such that a bar to the power of e times d is also equal to a bar. So perhaps you wonder why I get from this first formulation of the theorem to this statement, because it seems to change nearly nothing, but actually this will be used for cryptographic purposes. That is, a bar to the power of e times d actually is applying ciphering and deciphering, as we will see later, and we get a bar once again. Okay, so let's make a little proof of this statement. So we start from the theorem itself. That is, on one end, so a bar to the power of k times phi of n plus 1 is equal to a bar. And the starting point for the proof is that e and phi of n are coprime, that GCD is equal to 1. Then we use the already known Bezout's identity, stating that, let me remind you of that. So for all couple of numbers a, b, which are relative numbers, there exists another couple, u, v, such that a times u plus b times v is equal to the GCD of A and B. So we will apply this identity with E and phi of n. So here we use E instead of A and phi of n instead of B. And actually we will also change the name of the Bezout coefficients. Here, U and V, we will choose just different names, and you will see why, just in order to have names which are consistent with the previous presentation of the theorem. So, for E and phi of n, there exists a couple. Instead of U, I will use D. Instead of V, I will use K. It's just changing the names of the coefficients, but the Bezout's identity is still true, such that E times, sorry, E should be written in green, not in blue. E times D plus K times phi of n is equal to the GCD of E and phi of n, and as an hypothesis, E and phi of n are coprime, so E times D plus K times phi of n is equal to 1. So we can also, for the next step, actually, we can suppose that we can find some value of D which will be a positive number. And if D is a positive number, then K will be a negative number. Okay? You know that the coefficients, Bezout coefficients, have opposite sign as E and phi of n are positive numbers. So we can write this even if the extended Euclid algorithm gives us a solution where the D coefficient would be -1, there is a way to get a positive coefficient, just like for inverses. Okay, so now how do we go ahead from this? So actually, as E times D plus K phi of n is equal to 1, E times D is equal to 1 minus K times phi of n, with K as a negative number, is equal to 1 plus, let's call it K prime, actually it's minus K, but this is not important, with K prime as a positive number. Then we can use, once we have that, we can use the fundamental theorem of RSA. That is, if E times D is equal to 1 plus K prime times phi of n, then A bar to the power of E times D is equal to A bar to the power of K prime phi of n plus 1. Here I just change the elements in the sum, is equal to A bar as an application as of the fundamental theorem of RSA. So if you have something to remember here, is that you can always find a couple E and D for which A bar to the power of E times D is equal to A bar. The only condition, remember it here, is that this is true if E and phi of n are coprime. So we'll see in the next video what we can do from this statement, which is a very strong statement for RSA.